recording officially. And hello, Zoomers. Hello, Roomers. Vladimir is going to lead us through our formative assessment today. And I'm going to sit over here in my old lady glasses. So.
Thank you, Lisa. So, no, it's okay. Hi, people on Zoom. Hi, people in the classroom. I hope you are doing well.
I haven't done the screen share yet.
Oh, yes, of course. This is screen 2 or 1? 2? Or
so share 2, yes.
awesome. There we go.
You're good.
Awesome. Thank you, Lisa. I hope you had a great weekend, and today we will discuss just 2 questions from Formative Assessment 5. If I'm not wrong, yes, that's 5. 4. Great. Sorry. So just two questions. One of them related to an example, which is what I have here in the screen, and then I will briefly talk about dependency, and I will share a short story and some materials that I think can help you to understand this and to digest what dependency is, what this matters, and how, what options we have to take care of that issue, if that's an issue. Confirm your speaking is English. Amazing, it detected English, so now I can speak English for Zoom, which is good. Related to our question 1, I read all of your answers. They were pretty good, so good job, and thank you for giving us details about some of your examples. That was pretty helpful. So what I did for this question, I just copied and pasted some of your examples, and I double checked the details. But again, most of the examples were good, so thank you for that. Now, in this case, for example, we know that if in research we have something binary, like such as pass or fail a course, coded 0 or 1, we could use a logit or probit link function with a Bernoulli distribution to feed a binary logistic regression, right? Fair.
2 more links possible, though.
Yes. What are the other options for binary? Yeah, they can work with binary. Exactly. Yes.
The C log?
Yeah, exactly. Log and complementary log. C log when you have more zeros.
I will never remember which goes with which.
Yeah, to
I
me
think
that
you are
C
correct.
is for 0. Then I call it C log, and that C is for zeros. That's my
Okay, thank you.
my way to think about this. So yes, C log and complementary log if you have more zeros or ones. Then when we have something ordinal, such as pain severity, and we have levels or a Likert scale thing, we can use a cumulative logit link, and we could use a multinomial conditional distribution to feed our multinomial regression model. And here, we could also use at least one, I think, other 2 link functions, even if they are ordinal, I think. So, Mike?
Oh, I was just going to ask, could you also use a generalize for the ordinal?
Oh, yeah.
Okay.
Yes, I think that's possible, because we could use the generalized or baseline logit and adjacent logit,
Right.
depending on what we are interested in and what the submodels will be estimating.
Can we review those, how they work?
Yes, the complementary. The adjacent link function, in that one, your submodels will be comparing the subcategories depending on how to say this, not the gaps, but the differences. So let's say we have 3 categories. We will have 2 submodels. One of them will be comparing 1 versus 2, the other 2 versus 3. So it's adjacent because it's taking the adjacent values to create your submodels. Then we can also use the generalized or baseline logit, in which we select one of the categories as the reference, and the submodel will be creating differences between the rest of categories and the reference category. Okay?
And
Yes, the cumulative one, we are creating different submodels, and each submodel is predicting the difference between the lower versus the higher in that case. So we are taking cumulatively differences, for example, between 2 and 3 versus 1 or 3 versus 1 and 2. The general principle is when you have categorical variables, you will be creating submodels. What each submodel is predicting will depend on the link function you are using for that model. Is that good? Questions?
One thing I wanted to know, a couple of folks wrote a multinomial link function on their answers. Do you want to talk about that? Why that is not going to work?
Yes. Sorry, but where?
I had a couple of answers that said that they used a multinomial link function.
Yeah. Why do you think that's not correct? What is the multinomial? That's the label for what?
That's just talking about your model type, is it not?
About the distribution.
Right, yes.
Yes, for the conditional outcome. However, that's not working, or that's not doing what the link function should be doing in your model, because the conditional distribution is related to the outcome we are modeling, and the link function is doing what we need, is transforming our observed outcome into something link transform that is what the model is predicting. And that's why we have two scales in these models. One is data scale, which depends on the observed outcome, and we have model scale, which depends on the link function we are using to fit our models. So yes, many words, I know, believe me. I've been here for 3 years trying to understand all of these things. So if you have any questions, please just raise your hand or you can talk. And I'm reading the chat, people also. Then when we have nominal outcomes, yes, in this case, when we want to predict something categorical without a clear order, we can use, for example, a generalized logit or a adjacent logit link function to fit our multinomial regression model. In both cases, ordinal and nominal, we will be using the multinomial conditional distribution because we have more than 2 categories in our dependent variable. Okay? Then, what happens when we have counts? For example, the number of therapy sessions in a month, or a number of food sessions tried. In those cases, we can use a log link function now, and we have different options for our conditional distribution depending on some features or characteristics of our dependent variable. For instance, if we have over dispersion, we could use a negative binomial distribution instead of the Poisson distribution, which is the one that we can use by default. Also, sometimes we can have too many zeros, in which case we will need an additional submodel to predict those extra zeros, or we can use a Hurdle model to predict one submodel for, if any, zeros, and then we can fit our normal model or regular model with counts, in which we will be using Poisson or negative binomial. Then, here, what's the difference? Why are we using log? Let me ask you that. Why are we using log in this case? What's the main feature of the outcome that calls log here? Oh, exactly.
One lower bound.
Yes. More precisely, one bound. With log, with the categorical variables, we have 2 boundaries. And that's why we use those link functions. Now, when we talk about proportions, for example, the proportion of correct answers on a quiz, we can use again the logit function and we can use binomial or beta binomial distributions to fit our model. The difference between binomial and beta binomial is the flexibility. And in the binomial distribution, as similar to what we have in Poisson, we have one parameter to define the location of the distribution, the mean. So sometimes when we have over dispersion, we will need an stretchy factor, let's say, something else to model the dispersion in our data. So in both cases, in Poisson and binomial, when we need something else to catch the spreadness, we can move to negative binomial or beta binomial respectively to try to model our data. In both cases, we can use Pearson chi-square statistic to assess the differences between models, to perform relative model fit assessment. Finally, questions? Are we good? Great. So, finally, for question 1, when we have continuous outcomes above 0, for instance, reaction time in seconds, we can use mainly two options we're covering class. We can use the log normal or gamma conditional distribution, in which case we can use the identity link function or the log link function respectively. That depends on what you have, and I think that the gamma distribution doesn't allow zeros. So that's something that you might consider when you are trying to model something continuous using this type of models.
Yeah, if it has zeros, you need a zero-sum model to predict that.
Yes.
Turns into if and how much.
Yes, if you have zeros there and you want to use the gamma distribution, please consider your submodels for zeros. Hurdle or zero inflate, zero truncated.
For counts?
Zero inflated, I believe, is what you were describing.
Oh,
So for counts, if you want to do if and how much as a hurdle, then you need zero altered or zero truncated. So it's a count distribution. with no
yes,
zeros.
exactly. That's what I wanted to say. Thank you, Lisa.
Yeah, lots of words.
Yeah, surprising. So, how do you feel about this?
Here's
Good?
the class. Ta-da!
Yay!
Yeah, so this is like a summary of what we have seen so far in 3 months, which is a lot. So, now let me go to question 2. Oh yeah, the mouse is not working, but
Yeah, this happened earlier. It gets mad if it's,
Idle?
Yeah, like it shuts itself off and it gets mad and then I have to like unshare and reshare and all this nonsense. Okay. we're gonna
yeah,
let the
now it's
Zimmer in.
working again. Thank you,
Now it's
Lisa.
working again. Yeah, it's
Yes,
amazing. Do you want it full screen?
yeah, I can.
Okay, you do it then.
Yes, thank you, Lisa. So now, related to question 2, I was reading your answers. Well, I have a story and I have a comment. Yes. So the comment first. I read different type of questions. Most of them were close to what I think was what we wanted to hear from you. However, there were some details in words that would be good to discuss, especially related to what's dependency linked to, if that makes sense, sorry. But what do you think is dependency? Related to what mainly? And I have 3 options here. I read these 3 alternatives. Is dependency related to observations, outcomes, or predictors? Observations, predictors. I read outcomes too. I will pick outcomes. I will pick outcomes because, yeah, I read those 3 alternatives, and I think that, well, that's ambiguous. That's vague because we know that our predictors can be related to each other. That can be an issue in our models. That's collinearity or multicollinearity, right? So we know that our predictors overlap to each other. So maybe instead of treating those things as independent predictors, maybe they could be collapsed or one of them could be dropped. That can be an issue when we are modeling something. However, in this case, when we talk about dependency, we are mainly talking about residual correlation. That being said, to me, dependency in this class is mainly related to the outcomes, but also to the observations. And now I know that from the same observation, we can take outcomes and we can take in information for our predictors. I know that can be confusing, but I think that here we are using observations and outcomes interchangeable in some way, just because, for example, from the same sampling unit, from the same subject, from the same person, we can take repeated measures, for instance. But in that case, the dependency problem will be correlated to the residuals. So when I read those three options, and maybe you can say something, Lisa, we can have different type of dependency problems in our data, but here we are mainly interested in those related to residuals, right?
Yeah, I would say that dependency would be the right word to talk about relationships and predictors, because it's not necessarily a problem unless the relationships are super high, in which case then it becomes difficult to figure out their unique contributions because they're just butting heads. Like the issue here is, like, we're supposed to have independent residuals, and if you sample multiple outcomes from the same whatever, those are going to be related to each other, and that breaks the assumption, and that's what I think you wanted to show in this presentation
Yes.
that you've given before about.
Yes.
A little more detail as to how that
Exactly. So when I was reading your answers and I was thinking and processing all of these things, I remember that 2 years ago when I was taking one of the courses for the college teaching certificate, I had to work on a class, something simple, the professor said, to show students the things that we do in our field. So I thought that maybe multi-level modeling would be a good topic to talk about, and I created a set of slides, and one of the things that I tackled here was this idea of dependency and what options we have to address that issue in our data. So this is that presentation, and this is based on the idea that we are like in the middle of the semester and we are talking about something. So you can see that here I have like a list of topics, let's say for one semester, and I'm working in one of those things. So pretty good experience. I like it. And now I think that this can help us, and this can help you to pay attention to some of the things that I was mentioned before. So basically, when we talk about dependency, we are talking about this idea of correlation between the well, not correlation, but we are saying that some observations in our data are more related to each other than to the rest of the observations, and that's because maybe we have different measures of the same person, for instance. So measure 1 and measure 2 for person 1 will be more related to each other than measure 1 and measure 1 for different persons. And we have this type of clustering here. That's why this is also known as cluster data sometimes.
Can you give an example of what a cluster would be?
Yeah, the students in classrooms, the students in schools, the students in classrooms, schools, and districts. This idea of hierarchical units can help you to understand this, because when we have cluster data, we know that we have clusters, and within each cluster we can have different lower level units. Most of the time, for example, in multi-level modeling, we say that we have a 2-level model or 2-level sample, because let's say we have students in classrooms. So we have 2 kinds of sampling units, the schools and students, the students nested in the schools. We can also have patients in clinics, for instance, or items in persons too.
I have a question.
Yep.
So if you are only measuring within a class, not over classes, are you still worried about there being a cluster effect if you're only within? Now, between classes, I can say yes. This teacher has a style, this other teacher has a style, therefore, they're related. But if it's only in a class with the same teacher, do you need to worry about that cluster effect?
I don't think so,
Okay.
because we don't have other cluster to consider.
Okay.
So yeah, when we have only one cluster, and maybe sometimes we have, let's say, 2, 3, 4 clusters. In those cases, maybe that clustering effect can be a nuisance in our model, and we don't have to use multi-level modeling to to address that issue. We can use, for example, cluster robust standard errors or a fixed effect approach just to remove the dependency from our outcome and use traditional fixed effects model to predict our outcome. Just one.
So, Vladimir, are clusters considered to be different samples?
Oh.
Or is it just one sample that is considered to be as a cluster?
In the way that I think about it, they should be part of the same sample. But for instance, in multi-level modeling, we assume that the sample of clusters we have is representative of a population of clusters. But in both cases, all the clusters came from the same sample.
Okay.
If I'm getting that right. Lisa, what do you think?
Trying to understand that are clusters considered to be different samples because you talk about students in the school, students in districts, and students in a class. So are these all same samples or different samples? That's how I'm trying to make this.
Yes. All of our sampling units should come from the same sampling design. I think that we can say it in that way. So for instance, if I'm interested in conducting research about student satisfaction, let's say related to teachers' pedagogical practices, and let's say that I have different classrooms, my sample can be students in classrooms, and I will be taking that sample at the same time for every classroom, and I will be taking information for every student within that sample at the same time. To me, the difference, for instance, is let's say that you are conducting something similar. You have your sample, I have my sample, and then we try to merge those things.
Okay.
That would be another scenario, but to me,
So is that a cluster?
oh no, I don't think so.
The classroom is the cluster.
Yes.
Oh, the entire classroom.
Yeah.
Yes.
So you can think of it as multiple dimensions of sampling at the same time because you have differences among students and then you have differences among classrooms. Like which would be predicted by teacher things or like higher level variables. That would be the same for every student in that class.
Okay.
So could you also consider, if you wanted to say the impact of, say, taking this course prior to another course, could you say that like a cluster of students that took this would be like a cluster, and those who did not would be another cluster?
They would, but in that case, you just put in one dummy code as to which group you're in and you're done.
Okay.
Yeah.
You don't have additional clustering if you don't have like more than
So
one.
more-
Yeah, exactly.
Oh, okay. Very
Yes.
good. Thank you.
Devin.
Another question I have is like, so think about the students in the classroom, they can be from different grades, they could be in a heterogeneous like classroom. So like, can you consider the different grades as a cluster, or is that too far gone?
We could. However,
I would say the grade they're in is a classroom characteristic.
yes.
Because everybody in the room is in, fourth grade, like in my son's class. Or if it's mixed grades, like they do at Montessori or something, then that's like, are you single grade, or are you mixed grade as a classroom type? And then that's true of all the students who are in that room.
So
Yes.
the quality determines the cluster.
The what does?
The quality.
Qualitative description of the cluster.
Not quality, but naturally occurring groups is what I define a cluster as.
Okay.
So families are clusters, classrooms are clusters, people are clusters if you have repeated measures.
Okay.
They-
Can I say
They-
something that helps me think of it? Because when you just hear cluster data, I was just thinking of cluster grapes. And like sometimes you buy grapes from the store, like grapes are individuals, right? But
Yeah.
they grow on clusters.
Yes.
And
Okay.
sometimes when you buy the grapes from the store, it's like, oh, that's a good cluster of grapes. It's like they're just all perfect and like sour and just perfect. And then other times you get them and they're like squishy and bleh. That's a bad cluster. Like the characteristics of the cluster will probably affect each individual, but probably, each individual is still something
Got it.
distinct.
Yeah.
So I'm thinking like, I hear cluster, in my head I'm seeing grapes.
Okay. All right. Nice.
Yes.
Now, yeah.
You can think about clusters in the way that you think about grapes, and I think that's a good way to think about this, because at the end of the day, each cluster, if you could look into each cluster, you will see a collection of observations, and those observations will be more similar to each other compared to the observations in another cluster. And I didn't want to lead this conversation to cluster
I'm sorry.
multi-level modeling because that's next semester. Okay, Lisa will be teaching that one. But yeah, if you are interested, because this is common in educational settings, next semester Lisa will be teaching this in deep. So what I wanted to share, the other thing, just one more thing. Yeah, that's. No, I think that's okay.
Go through a little bit if you want.
Because consequences of omitting this issue. The main consequence is related to to our model for the variance, and we can have like two groups of consequences: substantial or statistical issues. When you omit the dependency between your observations. When we talk about substantial issues, we are saying that you are basically assuming that you have things that are independent when in fact they are dependent to each other. So you are missing in some cases sampling dimensions. Let's say that you have students in classrooms and you are omitting classrooms. You are saying I have students, which is something that I've seen a lot in my research area. And then they have some individual and cluster attributes in the same model, single level model. So they assume that treating all the information we have as independent is correct when in fact it doesn't. And then we can have statistical problems. Two things. One of them, our standard errors will be too small because we are the assumption of independent observations leads to have more information than what we should have in our data. So, of course, observations in the same cluster will be more similar to each other compared to other observations, but that's because they belong to the same cluster. So when we are not considering that, our standard errors will be smaller than they should be, because in the model it seems that we have more precision than what we have in our data if we would be considering the clustering structure or the hierarchical structure. The second issue is related to the conflated or smooshed fixed effect. Lisa, and I like that term, smooshed effect. And those could be fixed and random. An easy explanation would be you are mixing up things. You are mixing things up. You are saying you are feeding one model, but that model is not addressing the dependency. So you are saying that your student attributes, let's say, and school attributes have the same sampling dimension when that's not the case. And especially when you have student attributes, do you think that things shared by the group could be converted into a group characteristic? What do you think? Let's say that you have two classrooms. One is for adults, the other is for teenagers. Do you think that that individual attribute, age, could be converted into something for the classroom? Yeah, it could.
Very distinct.
It could. So the thing is, in the individual attributes can have systematic variance across clusters or across groups, and that needs another treatment. So when you are not considering that, the fixed effect or the estimates that you have for your individual predictors will be reflecting or will be a weight of two things: individual or within cluster differences and between cluster differences. So that's a mess. But that's all. So thank you so much. Hope you enjoyed the discussion.
All right, thank you. No, you're good. Yeah, so foreshadowing the clustered class. Let's get back here. Happy to answer questions, and everyone in here would be ready to take it. Do you want to come back and hang out in the fall? You know?
Yes.
I wish I could.
Yeah. Well, you can.
You could
can
drive
you can take the same class at Illinois eventually, hopefully. right?
or zoom in.
Yeah. All right. So in our case, though, we're not doing multi-level modeling in this class. That's a different class. But we are going to address dependency. And I put up a video for you to watch on Thursday. So my question then to the group is, how much of that do you want me to go back over as review or re-go over? So there's two different options. Review is review. Re-go over means talk about it as if you never heard it before.
I like review, but that's just me.
For me, because I had mine too,
Mm-hmm.
I was good all the way through the alternative covariance structures process. Then once you got into like how to handle dependency within the fixed effects, like that I learned to control.
Dependency in the fixed effects?
Sorry, see, clearly I didn't understand. Oh. Like the part at the end of the video where you were talking about how you handle dependency within the general linear.
Let me see here.
Yeah, so like the differences in effect size and cost outcome.
This part. You want to do this part again in terms of how to set up the model to have different fixed effects? Is that the question? Okay.
There might have been more too, but I know that part.
Okay. All right. How about I hit some highlights? Would that work for folks? That sound good?
You can ask questions along the way.
Yeah. We'll do that.
Yeah.
So, I'm not going to do with the matrices again. Is that all right with you? No one likes matrices.
I loved the matrices.
You like the matrices?
I found them really helpful last semester, and because I remembered last semester,
You're in
so
lecture
I did
6.
this. So.
Say what?
You're in lecture 6.
I am in
5.
5.
Okay.
Yeah, this is slide 6 of lecture 5. So we haven't done this in this class yet. I'd put it up, and then I put up the video from last year that started it off. But the key idea here is that, let me jump in here to slide 6 here. I'll hit the highlights, okay. So this matrix at the bottom is the point of the story. The rest of this you can probably safely ignore. The idea that this is person 1, this is person 2, this is person 3, this is person 4. So it's like each person has a row and a column because it's a square matrix. And the fact that these are all zeros means this is a general linear model at this point. So we're leaving generalized land for a week or so, and then we'll come back because I'm starting with just multivariate straight up with, everything is pretending to be normal. In a standard general linear model, we say the residuals are unrelated across people. So there's no pockets of correlation because we're assuming independence, no clustering. So that's why all of these things are 0. And this is sigma squared sub e, the residual variance of the model. And because we're using a normal distribution at this point, there's only one value. The normal distribution has a variance. It's assumed to be constant. And it's assumed to be constant across people as well. So that's why this is the same thing across. So when we have data that have some kind of dependency, so repeated measures is the case that we're going to look at in our example, where I have a family as the unit of sampling, and I have responses from a mom, a dad, and an adult child. Well, if I ask about, attitudes or behaviors or opinions, people from the same family may be more related than people from different families. Just like kids from the same classroom may have outcomes that are more related than kids from different classrooms. It's the same premise. But in the case of what I would call a balanced design, in which there's only distinct possibilities, so mom, dad, kid in my example, or pre-test, post-test follow-up, like when there's only a fixed set of possibilities, then you can just say, hey, let the outcomes from the same sampling unit be related. You can just tell your software to do that. And so that changes it so that these zeros in some spots turn into something else, a covariance, among the outcomes from the same sampling unit. So in order to do that, we have to switch from a standard univariate normal definition of height. So this is back from I think lecture 0 when we first started talking about this. Maximum likelihood is essentially the likelihood of each of these observations given the model parameters where each person has one y. We have to hack this so that each person or each sampling unit more broadly has multiple y's. And then we get the joint height of a person's set of y's as the number that comes out of the formula. So we have to switch from univariate to multivariate. In order to do that, though, we got to trick our software. So this is one step that will be brand new to most folks. We have to start with a data set that is in what is known as wide or person format, where it's 1 row per person, and I have repeated measures. In this example, I have time 1 and time 2. In order to be able to predict both of them at the same time, using standard software, I have to trick it into putting them in one column. So this process is known as reshaping. I call it stacking. And the result is what is known as a long data structure here, in which it's 1 row per outcome per person instead. So that's a different animal. So now I have person 1 taking up 2 rows, person 2 taking up 2 rows. I need a new index as to which occasion it is, and that was previously indicated by the names of the columns, so I would have to create that. This is an example of what would be a time-specific predictor, and so this is going to be essentially the dummy-coded version of time. So 0 would be pre-test, 1 would be post-test, and then y is stacked in here. So we have pre-test, post-test, and so on. Then we can predict 1 column. Okay, are you with me so far? So what's going to happen is we are going to essentially create switches in how we set up the model to say, if this is this outcome, here's my fixed effects. If it's the other one, here's my fixed effects. So we're predicting, in this example, it would be like pre-test and post-test simultaneously, but we're doing it with different fixed effects for each potentially, and that way we can measure change. So I think there were a couple of you who wanted to look at change as part of your homework forward. I said, you can't do it yet because we haven't got there. Well, this is where it starts. So then changing the expectation to multivariate normal, we create these little pockets of relationship. And this pattern, by the way, is known as block diagonal. So inside the blue boxes would be outcome 1 and outcome 2 for somebody, the first person, outcome 1 and outcome 2 for the next person, and so on. So people are still independent. That's why we have zeros everywhere else. But within a person, the outcomes that they have get to have a relationship. And this is covariance, which is unstandardized correlation. So these are variances and these are covariances. So then the question is, what shape essentially do these little pockets take? Do the variances need to be different across time, or can they be the same? And if I have more than one covariance, do they need to be the same across time or different? So no covariance would look like something like this in 3-dimensional. If there is a covariance, it starts to look like a taco. So there's like that's what it looks like to me.
Stegosaurus back.
Yeah, a dinosaur back, I don't know, taco, rainbow-colored taco, I guess, like a Skittles taco. I don't even know. That's probably a thing you can buy at Taco Bell by now. Matrices, math, point being we are switching out what used to be one residual variance, just the one, with a matrix, because now we need to keep track of all of them as well as their covariances. But still at the end of this, one number that is the height of a person's set of outcomes. That's what these formula gives you. And so the job of the model is still to make the data the tallest collectively. That hasn't changed. What has changed is we're now adapting the formula for height to allow relationships among the outcomes from the same sampling unit. That's the big picture. Missing data. Basically the rule is every row of your data set has to be complete with respect to all variables that are in your model, or it will get dropped. So this is an advantage of doing multivariate analysis using likelihood estimation relative to what it would be in traditional MANOVA, for instance, or repeated measures ANOVA. In those models, they're based on sums of squares. The sum has to have all the pieces to it in order to work. So if you have somebody who came at pre-test and they never came back at post-test, if you use least squares estimation, you can't keep any of their data because their sum is going to be incomplete. Whereas if you use likelihood, you get to keep whatever you do have. So it's better for power, it's better for inference, because if you kick out all the people who didn't come back, then your sample is limited to like the conscientious people that are like reliable, responsible, and who cooperated. And that is not necessarily a good subsample of like the universe that you want to be able to talk about. And that is even worse as you get into things like aging, right? Like if you have a longitudinal study of older adults and you only analyze the data from people who made it all the way through, you're getting like the super seniors, for instance. If you have high school and you're looking at kids who are at risk, and you don't include the ones who dropped out, right? Right, that's a problem. So that's what's known as informative missing data, right? If people drop out for reasons, then you want to be able to capture as much of the data as you possibly can and potentially try to control for that kind of thing. So, yeah. And then this is the other class. So there are other options in terms of what to do with missing data. I will show you an easy way, which is to pretend that the missing information for a predictor is actually an outcome. And so long as you're willing to make some distributional assumptions, we can make that work. So I will show you how to do this in path models. But missing data is the biggest reason why I would recommend doing multivariate type of analyses, meaning predicting multiple outcomes from the same unit using likelihood estimation as opposed to ordinary least squares. And that is why I don't teach repeated measures ANOVA in intermediate, because I knew I would have to open up this entire can of worms and I didn't want to go there. So we're going to do it now. All right, so this is an example then with 3 outcomes per person. And then the question is, does variance at the first one, does it need to be the same as variance of the second as the third? And then the covariances here, should these all be the same or should they be different? And the good news, you already know how to decide this. So whenever we've had questions about distributions and their fit, like should I use Poisson or negative binomial, or should I use beta binomial or binomial? How did we answer those questions?
LRT?
Likelihood ratio test. Guess how we're going to answer this one? Likelihood ratio test.
Yay.
Do the data get taller if I add differences in covariance, differences in variance? If they don't get taller, then it's overkill and you don't need it. So I want to give you a couple options in terms of what would be reasonable for repeated measures kinds of data that don't depend on what kind of repeated measures. So like these would work for most cases. One is called unstructured. And the easy way to remember this is that everything gets to be whatever it wants. No constraints whatsoever. The variance of the first outcome is different than the variance of the second is different than the variance of the third. And the covariances are different too. So this is what is known as the multivariate approach to repeated measures ANOVA, or MANOVA, in the ordinary least squares language. In structural equation modeling, this is also known as the saturated H1 model. So this goes by a bunch of different names. So if you only have a couple outcomes, like 2 or 3, this is fine. The problem comes in if you have a bunch. So what if I have like 10 outcomes per person? Could I do that?
Yes.
I can do that. Now, how many different terms would I have to estimate? Too damn many is the answer. And here's the formula by which you can figure that out. So if I had 10 outcomes per person, that's n here, n plus 1, so that would be 10 times 11, that's 110, divided by 2, 55. So that is 55 things that the model is trying to find as part of its search process before we even start talking predictors. At a minimum, you need 55 people to pull this off, and lots more, ideally. So that's where, once you have lots of repeated measures, this starts to fall apart. If you only have a couple, this is fine. And in terms of likelihood, this will be the tallest. Like, this is as good as it gets. Question?
Is it meaningfully the same thing to do an unstructured R matrix or to add a fixed effect predictor to your model for a person? Because that would also be like saturating. You would basically be doing, especially if you've added interaction with a person and all of the other variables.
Okay, the question was, is this analogous to adding in a fixed effect of person?
Especially with an interaction.
Well, as a main effect, the answer is no. The adding in a main effect of person, so as, like, that would be one way to control for dependency, is just control for who's who. And that would solve the problem statistically, but it would be really sad from an interpretation point of view, because you'd be like, well, why is this person higher? Oh, because they're person 180.
Okay.
Like, what am I going to do with that, right? But if you were in a setting in which you cared about that, let's say you're in a treatment context and you have treatment for 5 people, and you want to be able to talk to, Bobby's parents about how Bobby is doing as person 180, then that kind of specific inference would be useful. Or if you're trying to predict who's going to win the NCAA tournament in basketball, and you want to have a fixed effect for Gazanaga or whatever the hell it's called versus KU and all the other ones. So that's one of the things my husband likes to do, is create predictive models for sports. And he actually predicted, I think, Gonzaga? What is it?
Gonzaga.
Gonzaga. He predicted that they would win the year that they won with his models.
Cool.
And then he got interviewed by like local radio stations and TV shows because they wanted in on that. But in that case, a fixed effects approach is appropriate because you want to talk about what's going to happen to KU, what's going to happen about, Carolina, what's going to happen to Duke. But in research, it's more like we want to be able to say people are higher because, and then relate that to some kind of predictor, not just being person 180 or being KU or whatever. So long answer, haven't answered your question yet. A fixed effective person as a main effect is analogous to a pattern that says all the variances are the same and all the covariances are the same. So that's another choice that's on here. That's what's known as compound symmetry. That's also known as the univariate approach to repeated measures in a least squares sense, and that's a constant correlation. So if a constant correlation fits and is reasonable, then putting in a fixed effective person would be fine. But if it doesn't, then it will be not controlled for enough to the same extent. But fixed effective people wouldn't allow you to answer research questions about why people differ. And I think that's the bigger limitation.
So if we use an unstructured alternate covariance structure, we can still answer questions about why people differ.
Yes.
While also accounting for the fact that they do differ.
Yeah, so these are the three choices essentially that I want to show you. Everything's the same. Variants are different, but the correlation is the same, or everything's different, like unstructured. Those are the three choices that would work in this context. And yes, you find the one that fits relatively best, so unstructured is going to be best. But then the question is, are the other ones good enough? Are they not worse in terms of how tall they make the data? Then you can answer questions about why people differ from each other, as well as questions about each of the outcomes. So does this predictor have the same effect in this condition as that one? Does the effect of this predictor change over time, for instance? You can answer those kinds of questions. And then just, is there change over time in the first place, right? So from pre-test to post-test, did people change on average? So this requires different software options that have the capability to say what happens to this pattern. All the same, all different, or somewhere in the middle. Okay, like that. Likelihood ratio tests, that's what we can do. And example of repeated measures from a long time ago that I still haven't had a chance to get back to. Yay, pandemic semester. All right, let's see, do I want to talk about this? I think we got, yeah, this is the part that I skipped. Let's go to, no, I don't want to do that yet. Let's go to the other part that was the second half of the video in terms of strategies for specifying multivariate models. Can we talk about that? Yeah, why not? So there are two different ways, this is slide 27, to set up these models. And so which way is going to be more useful depends on how you're thinking about the outcomes from the same whatever. So it'll be people from the same family. In the example we're going to see more generally, it would be repeated measures from the same person or sampling unit. So if you're thinking about it in terms of examining mean differences, so you want to know if pre-test differs from post-test. You want to know if people do better when they're studying listening to Metallica versus classical music, like repeated measures of different kinds, and you want to understand the differences. And then setting up the model in the usual way that we're used to, where there's one general fixed intercept, and then you have slopes that say, what's the change from like pre to post, or what's the change from condition A to condition B, that would be just fine. If you're thinking about it in terms of if you're thinking about it as like different outcomes, and you're not interested in the changes between them, then this is going to be less useful. So this is also optimally a way to ask questions about differences in effect size across outcomes. So for instance, if I have an intervention study and I'm trying to help people with their levels of depression, I might also measure things like well-being and anxiety and other stuff. I might answer a question, does this intervention have a bigger effect on depression change over time than on anxiety? In order to answer that question, both the outcomes have to be in the same model, and you already know how to do that too. That's a difference between slopes. So a -1, 1, in like a GLHT or a Lincom statement. Same exact machine rate. You already know how to do it. In that case, it would only be meaningful to compare slopes if the outcomes are on the same scale, because slopes are unstandardized. So you'd want to maybe z-score them or otherwise make sure they're on a comparable scale. But if you're thinking about the outcomes as separate things and you're not as interested in the changes between them, then setting up the model differently is going to be a little more useful. And so I want to show you how to do each of these and sort of how they map onto each other. That way you have all the tools at your disposal to do it however you want, what's going to be most useful. And I will say that the idea of having pre-test predict post-test and only having post-test as the outcome is a bad idea in a lot of cases. And here's an article about why, if you're interested in that. So I do not like those models. I would not encourage you to pursue them. So I think I can, yeah, go ahead.
The one at the bottom that you don't like, is that the kind of model that's used by a lot of the, or at least was used before the Department of Education got cut, to like assess school districts, because they would do pre-test for kids and then they would try to predict how much they thought the student should improve at post-test, and then if somehow the student didn't improve as much as they thought, they would blame the teacher or the school?
Those are, yes, I think you're talking about value-added models, potentially.
I don't really know what I'm talking about. I've just heard that that is a problem with how school districts and teachers are assessed.
Yeah, so if you have teachers that over multiple years, so you can observe teacher changes, and then you have students over multiple years, there are models that purport to be able to pull that apart and say, what is the value that this teacher adds to a student's outcome? And that's all based on multi-level modeling, either with fixed effects or random effects. And the problem is that those things are phrased as deviations from expectation. And so your model has to be right in order to say those deviations are meaningful. And because students are not randomly assigned to classrooms, you can't really say that. But let me give you a quick example. So let's say that this is pre-test. Let's say that this is post-test. And let's say that everybody grows. A little wrinkly lines here, but to the best of my ability, everybody grows. So if I put in this variable right here as a predictor of this one, what's going to happen? It's going to capture all the variance. So it will look like there is no change because there's no variance left over, but there is change, clearly. Everybody is changing like in the same way. So in contrast, if you have something like this where there is change, but like the change is not necessarily predictable from where you were to begin with, if you get some weirdness like that, then it's like it will try to ascertain how much change you have relative to what the model expects based on where you were here. So it's not change, it's weirdness. It's residualized change. And I don't think a lot of folks understand that. And so I thought this article did a good job of explaining it, which is why I linked it there. So if you have pre-test, post-test data, I would highly encourage you to set it up so you can look directly at change. And the only way to do that is by predicting both in the same model so that you've got access to all the pieces of information at the same time. Okay, does that help? Maybe? Try not to make it worse. So this is just a couple slides to talk about the difference in effect size, because this is something folks don't necessarily understand. So let's say that I have a predictor, and it's significant in predicting outcome A, and it's significant in predicting outcome B. Just because they're both significant, meaning I've crossed the arbitrary line in the sand here, I can't say anything about whether those effects are the same. It could be that one is much larger, and it's really this discrepancy is what you want to isolate here. Likewise, something like this. A predictor is significant for outcome B, but not A. Does that mean those slopes are different? No, it doesn't. So we want to test the differences. That's the key idea. So here are two different ways of setting up these models. And they both require dummy codes that are going to work as switches, turn things on and off. So let's say that I have 3 outcomes I'm predicting simultaneously. Like this could be pre-test, post-test follow-up. This could be how you perform in different writing tasks, for instance. Yeah, right? Just putting it together. So I have to set it up. First, I need a DVA demicode binary variable that is a 1 if the row of data I'm currently predicting is A and a 0 otherwise. I do the same thing for B. I do the same thing for C. A general intercept parameterization would make one of these outcomes the reference, kind of like a nominal model in that same regard, and then we have differences to get from the reference outcome to the others. So then any fixed effects for the non-reference outcomes, DV stands for dependent variable, by the way. I had to come up with some shortening here to make it fit.
I just pieced it like, oh yeah, that's what DV is.
That DV is dependent variable, meaning outcome. The differences would be found as linear combinations for any non-reference DV. The other way is to set it up where you don't have a general intercept. You have one per outcome. And this looks weird at first, but once you see it, it makes a lot more sense. And this is what happens in path analysis. We will have separate outcome boxes that we're going to predict and then examine relations for each one of those. So under the hood, when you tell your software that you want a variable in the model to be treated as categorical. So that's the class statement in SAS, that is the I. prefix in Stata, and that is a factor variable in R. That is what it's called. Under the hood, what it is doing is this coding scheme. It is creating the 3 demicodes for you. So then you have access to these internal variables, and you can use them to say, I want this slope for this variable and this slope for that variable. The only thing that you have to pay attention to is who is the reference. So in SAS and SPSS, the highest category in a factor variable is the reference. By default, in Stata and R, it's the lowest. And you can change these around, but results will differ across packages if you don't pay attention to this. So here is a general intercept version. This is most useful if you're interested in differences between your outcomes. Like, is one task harder than another? Are scores different at post-test than pre-test? If that's what you want to know, set it up this way. So in this example, C as the outcome is my reference outcome. So I have 2 subscripts here, an I for person as usual, and D for which DV. So I have a beta 0, 0, because this is my fixed intercept, and then I have a beta 01 and a beta 02, because these are for the reference DV, for the A DV, and then for the B DV. So 1 and 2 are indexing A and B. So that means the fixed intercept, same rule as before, right? What's an intercept? What's the definition of an intercept? We'll go back old school for a minute here. The expected outcome when all the predictors are 0. Doesn't matter what class you take from me, that definition will never change. What changes is the context. So if I think about it this way, when are all my predictors 0? Well, DVA when it's not A, when it's not B, that only leaves C. So therefore, my fixed intercept is going to tell me what the intercept is for C specifically. Beta 1 gives me the difference of how A differs from C. Beta 2 gives me the difference of how B differs from C. And that means that if I want A versus B, that's a linear combination, where the A1 would be the -1 in the code and the B1 would be the 1. So B minus A in that case. If I want to get the model implied intercepts for the other ones, then it's a linear combination of the fixed intercept for C plus how it differs for A or plus how it differs for B. Question? Question? Yeah.
Yeah, no, that was a question.
Okay.
I am puzzled by the difference between this and the difference between nominal regression
Mm-hmm.
and logistic regression. Because when we have nominal regression, we're also predicting things, and we often use dumpy indicator coding. But for that, we use submodels.
Mhm.
For this one, it's not like one thing we're predicting with multiple categories within that thing. It's like we're predicting totally different things, so we can't use submodels. Is that right? But I think the idea of like we can find the differences between our outcomes with linear combinations, that's true for ordinal regression, nominal regression submodels, and it's true for this one, where basically we have like 3 intercepts. The first 3 fixed effects are 3 intercepts. Whereas if you have a nominal regression, and it has 3 categories, the first 3 would also be.
Okay.
No, there's only 2. If you have 3 categories.
Yes. Okay. So let me capture that for the recorder and the Zoomers. So the question was, is this analogous to nominal regression? Because it sort of sounds like that, like I have a reference DV and that kind of thing. The difference is that in nominal, you have 1 answer. You picked 1 category. Whereas this, I've got 3 answers. How I did in A, how I did in B, and how I did in C. I'm predicting all of them simultaneously. But I'm using which is which as fixed effects to allow me to examine the changes across them in this version of the model. I don't know if that helps or not.
It does help. It's hard.
It is hard, yes. It is hard, yeah, I'm not gonna lie.
So if
Yeah,
you're looking
here's a
at
predictor.
3 different outcomes, 3 different,
Mhm.
the first 3 fixed effects are your intercepts. And then on the next slide, you're going to show us that we add
Not
slopes.
quite. Okay, so let me stop you there. These are not all intercepts.
They're not intercepts.
No,
These are slopes.
these 2 are slopes and this is an intercept. But what they are differentiating is which outcome is which.
Can I quickly add something?
Yeah, please do.
Pretty much the same thing that you had mentioned about pre-well and post-tests.
Mhm.
So the intercept would be the reference point. The slopes would be pre-well and post. That will determine the difference with the reference point that we can measure the difference. This is somehow helpful.
Yeah, I think that's a good way to look at it. So let's say that you're interested. So I'll give you an example study. It was about people who were trying to lose weight. And there was one group that had like a traditional weight loss program and another group that had like a better new one. Okay, so they wanted to know if the new program resulted in people losing more weight. So they had a pre-test weight. They had some program stuff. They measured them after it was over. And then they measured them like maybe 6 weeks after that to see if they maintained, right? And so the goal was to not gain your weight back. And so in this case, like if this was, let's say that the reference outcome here was where you started, then beta 01 would capture how much weight did you lose during the program. And then beta 2 would capture like how much did you end up losing like in total, like net, like how much did you, like the difference between pre-test to follow-up. And so each of those slopes would be meaningful because we want to know, is beta 01 bigger if you're in the new program? Is beta 02 bigger if you're in the new program? So this is set up to get at differences. One of the examples that I put as a bonus, which I won't have time to do, use this approach to talk about body image. So there's a scale that basically it's like stick figures that have different like sizes, ranging from like really skinny stick figures to larger ones, and they're numbered from 1 to 10. And the people are asked 2 questions. Which one do you look like? So like, I'm number 6, you know. Which one do you want to look like? Okay, so in that case, the discrepancy between actual and ideal is what the study was focused on. And they wanted to know if that discrepancy was different as a function of gender or age or, you know, personality or what have you. So in that case, like beta 01 would capture the discrepancy directly from one outcome to the other. So from ideal to actual, or from pre-test to post-test. So if the difference across your outcomes is the thing you care about, this is the way to set it up to get that directly. So if we enter a predictor into the story, now we want to predict 3 things, right? 3 slopes. So these models get big real quick. So in this case, if I start with this model and I add this stuff to it, now these things look like interaction terms, and they kind of are. So we have what I would call the main effect of X right here. And that is only the effect of X when these things drop out, when the moderating variable is held to 0. So therefore, this must be the effect of X in condition C specifically for that outcome. And then beta 1 tells me how the effect of X differs if I'm talking about predicting A instead of C. And beta 1,2 tells me how the effect of X differs if I'm trying to predict B instead of C. So this would be like, is the discrepancy between actual and ideal higher for women than men. That's what they found in that study. Or for younger people than older people, or what have you. So this is moderation of change, or of the differences between outcomes. And I think that's what you had with your tasks, right?
I don't think we did it quite like this. Yeah. So for these two, the second section starts with a plus sign. So we
Yes.
literally just add that whole row
Yes.
to the next one.
Yeah, so
we
this,
have 6 fixed effects.
yeah, so technically speaking, these 3 effects right here create an empty model. And I know it looks crazy to say that because it's like, how is it empty if I have predictors? But you kind of don't. What you have created here is 3 different means, one for each outcome. So from that perspective, you haven't predicted each outcome, you've just said which is which, allowing them to have different means as a starting point. Now we would have one predictor, but one for each outcome, allowing it to have a different effect on A than C and on B than C. So this version of the model, this is what it would look like in SAS. This is what it would look like in Stata. So I have Y as my generic outcome. I have DVA and DVB as main effects. That gives me the differences between conditions. And then I have X as a main effect, and then interaction terms that say how the effect of X differs if I'm predicting B instead of C and A instead of C. And in R, it would look like this. And so there's two ways to do this. Come back here. Here we go. Nope. So in the first one, I'm writing out all the individual dummy codes, A's and B's. In the second one, I'm letting the program do it as a categorical variable for DV. So the code is shorter, but it's less transparent because it's using the internally created binary contrasts to represent like DV. So you wouldn't know just looking at this code how many fixed effects are in your model. You'd have to know how many DVs you have to figure that out. And then, so we're going to be using the routine mixed in Stata to do this, which stands for mixed effects models. And in R, we're going to be switching packages to a package that's designed for multi-level modeling, and the function within it we're using is GLS for generalized least squares. It allows you to have repeated measures and to have correlations among your repeated measures. The question then, where I have the question marks here, is what kind of pattern in that R matrix? All variance is different or all the same? All covariance is different or all the same? So that is something we would determine with the data. All right, 311. I don't want to do the next one yet because it's going to be confusing. So if I can wrap this up into a nice little bow, everything you've learned is going to show up in these multivariate models. The only extra thing that you have to think about that we haven't thought about is what kind of pattern are the variances and covariances in? Do they have the same variance across repeated measures or not? Do they have the same covariance or not? And if you're like, I'm just going to use unstructured and call it safe, good. Do that. It's fine. And that's why I told you, like, just use unstructured. Because the worst it can be is overkill if you don't have that many outcomes. Now, where this falls apart and why you would want to take, like, the multi-level modeling classes is what if people have all different kinds of outcomes? In terms of, you don't have pre-test, post-test follow-up. You have, like, whenever they happen to show up and give you data. Then it's not nice and tidy ABC. Or in classrooms, we don't have kid A, kid B, kid C. Each classroom can have different numbers of children. So that's unbalanced, and that's what those types of models are designed to handle. And this is a balanced case where the set of potential outcomes is the same for everybody. And they can be missing. So if you have somebody who gave you data in conditions A and B, but not C, you can predict their A and B outcomes. You just can't predict their C. That's okay. It's better than limiting your sample to only people who have complete cases. So, all right, 313. I can tell by your faces you're full.
But less confused than I was on Tuesday.
Less confused than last week? Okay. We're heading in the right direction then. Yeah.
This may be outlandish, but since we're like talking about structures, wouldn't this also map onto factor analysis?
Yes, actually, factor analysis is another kind of pattern. That's all I want to say about that right now, but I can give you the details. But it creates a pattern. Yeah, factor loadings create a pattern of correlation. All right, then let us know if you need help figuring out homework 4 that is due next week. Office hours tomorrow and Friday.
Yes.
Yep, as usual. Yeah, that's it. Thanks for being here. I will see everybody on Thursday. How's that sound? Excellent. Bye, Zoomers.
So you're not going to the conference?
I am not going to the conference. Nope.